Malware is a word that will be top of mind for you if you're in the business of securing your enterprise. If it wasn't already complex, it becomes all the more challenging if you add just one more word to this: encryption. I'm Sarav, and I'm a distinguished engineer in the enterprise networking group in Cisco. I'm going to be talking to you today about Encrypted Traffic Analytics, or what we call in short as ETA. ETA brings together the power of the network and security to solve some very hard to problem problems for customers. So here's what we're going to do. I'll first talk about why we need encrypted traffic analytics, specifically the trends that we've observed and the problems that it opens up. I'll then follow that up with how we will be solving these problems and what we've done from a productization perspective. We will then do a demo of ETA and then round it off with the key takeaways from this presentation. So let's get started. Why do we need ETA? There are two key trends that we've observed in the enterprise that warranted us to take a deeper look at encrypted traffic. The first key trend is around the increase in the amount of encrypted traffic. As more businesses embark on their journey of digital transformation, a significant number of services and applications use encryption as the primary method of securing their data in motion. Encryption technology has enabled much greater privacy and security for enterprises, and therefore enables them to use the internet to communicate and transact business online. Between July 2015 and 16, the amount of encrypted traffic increased from 21% to 40%. That's close to 90% year-over-year increase in the volume of encrypted traffic. Gartner predicts that over 80% of all web traffic will be encrypted by the year 2019. However, the IT spend on encryption has not kept up with this increase in the volume of encrypted traffic. This increase in the volume of encrypted traffic opens up an opportunity for adversaries with malicious intent. Encryption has turned out to be a double-edged sword, and encrypted threats are a growing attack vector. Increasingly, encryption is allowing cybercriminals to hide malware, ensuring that it remains undetected in the enterprise as it propagates. What works for unencrypted traffic, like signature matching, will no longer work for encrypted traffic. Traditional threat inspection with bulk decryption, analysis, and re-encryption may not always be practical or feasible for network performance reasons. So therefore, the second trend, not surprisingly, is the increase in the percentage of malware that leverages encryption. Our own analysis of threat grid data shows that the percentage of malware using encryption hovering around 30%. Malware that exclusively uses TLS has increased from about 0.5% a year ago to about 4% now. A recent study showed about 41% of the attacks leveraging encryption to evade detection. And Gartner believes that half of all malware campaigns in 2019 will use some form of encryption to conceal malware delivery, command and control communication, and data exfiltration. Another problem is that there is a lack of enterprise-wide visibility into encryption strengths that exposes vulnerable implementations. Such implementations are susceptible to man-in-the-middle attacks. So what do we need to solve this problem? We need to be able to identify malware in encrypted traffic without decryption. Why should we avoid decryption? Because decryption compromises on the privacy of the end user. We will need to walk this fine line between security and privacy to solve the unsolvable, and that is precisely what ETA enables. So let's look at how we solve this problem, which forms the basis for this pioneering effort in the industry. The fundamental building block for encrypted traffic analytics is enabled by research done by Cisco fellow David McGrew and Blake Anderson. As we began developing the techniques to fingerprint and identify malicious encrypted communications, we performed the first comprehensive study of malware's use of TLS. We identified interesting data features and collected this data from millions of benign and malicious TLS sessions. Our core insights, such as enterprise traffic typically using up-to-date cryptographic parameters and malware typically using older and weaker cryptographic parameters, led to the development of state-of-the-art machine learning classifiers that are able to detect malware in encrypted traffic. With this approach, in our research, we have been able to identify known malware with over 99% efficacy with a very low false positive rate. All this research has been published as papers which are available online. So now let's look at the specific data features in more detail that make this detection of fingerprinting possible. There are two specific features that helped in fingerprinting the malware: the initial data packet and the sequence of packet lengths and times. The initial data packet of a flow is a critical piece of information that helps us learn more about the TLS client. While the actual TLS application session is encrypted end-to-end, the initial TLS exchanges happen in clear text. When a TLS connection is established, the client will send a client hello packet to the server. This is followed by a server hello message from the server to the client. It is the client hello and the server hello packet that we'll be looking into as part of the first data packet in each direction. The TLS client message provides two particularly interesting pieces of information that can be used to distinguish between different TLS libraries and applications. The client offers the server a list of suitable cipher suites ordered in the preference of the client. Each cipher suite defines a set of methods such as the encryption algorithm and pseudorandom function, which will be needed to establish a connection and transmit data using TLS. The client can also advertise a set of TLS extensions that, among other things, can provide the server with the parameters needed for the key exchange. The cipher suite offer vectors can vary in both the number of unique cipher suites offered and the different subgroups offered. Similarly, the list of extensions varies based on the context of the connection. Because most applications typically have different priorities, these lists can and do contain a great deal of discriminatory information in practice. As an example, desktop browsers tend to favor heavier weight secure encryption algorithms. Mobile applications favor more efficient encryption algorithms, and the default cipher suite offer vector of clients bundled with TLS libraries typically offer a wider range of cipher suites to help with testing server configurations. The sequence of packet lengths and times is a second feature, and this provides a unique and innovative means to identify malware in applications. The malware application typically performs some operations on the client, including gathering data and exfiltrating the data or communicating with the command and control server, thus creating a pattern that is really distinct from normal browsing patterns. There is a relationship between the malware or benign application behavior and the message lengths and the times. When the application, which is the server or the client, is doing some operation like reading or writing to or from the disk, that drives the time between the messages, and the amount of data communicated drives the length. To understand this a bit better, let's take the case of the Bestefera malware. This family belongs to a family of malware known for key logging and data exfiltration. It attempts to collect a user's online banking data and sends them out to a control server known for key logging and data exfiltration. The lines above the horizontal line that you see in this picture represent the size of the packets from the client to the server, and the ones below represent the packets from the server to the client. The red lines initially represent clear traffic, while the black lines represent the encrypted traffic. So if you look at what happens in the context of a Google search, you will see that after you type a search string, you'll see a whole bunch of responses from the server to the client. The single lines represent the autocomplete responses that you get from Google, following a lot of packets that represent the page refresh. In contrast, if you look at the communication pattern for Bestefera, you will actually see a few packets from the server to the client, but a lot of packets from the client to the server, which is in line with the model of operation expected for this family of malware, which focuses on data exfiltration. You can also see from the message from the command and control server, which is encrypted in this case. Most user applications, and by extension a large number of TLS connections seen in the wild, use popular TLS libraries such as Boarding SSL, NSS, or OpenSSL. These applications usually have unique TLS fingerprints because the developer will modify the defaults of the library to optimize their application. To be more explicit, the TLS fingerprint for a client from OpenSSL 1.0 will most likely be different than an application that uses OpenSSL 1.0 to communicate. That is also why Bestefera's TLS fingerprint is both interesting and unique. It uses default settings of OpenSSL 1.0 to create TLS connections. Most user-level applications, and by extension a large number of TLS connections seen in the wild, use popular TLS libraries such as Boring SSL, NSS, or OpenSSL. These applications usually have unique TLS fingerprints because the developer will modify the defaults of the library to optimize their application. To be more explicit, the TLS fingerprint for S-Client from OpenSSL 1.0.1 will most likely be different than an application that uses OpenSSL 1.0.1 to communicate. That is also why Bestefera's TLS fingerprint is both interesting and unique. It uses the default settings of OpenSSL 1.0.1 to create its TLS connections. I know you might be wondering why this approach is successful. We're looking at the actual behavior of the data on the wire generated by the application, that is, how it is sending and receiving data, and we couple that information with the actual library used by the application on the endpoint that generates this data. So if you look at the second pattern here, there's really not a lot of benign reasons for that pattern where there's a lot of communication from the client to the server, but it sure is possible. For example, when we upload a file to a server like Box or something, we will actually be able to see this pattern. But then when you combine this with the fact that it has a specific library, then the possibility of this being benign reduces even further because we don't see something from S-Client to the open internet. So what did we actually build to productize this solution? Let's look into what we did to take this awesome innovation to market. As a recap of the specific problems that we're trying to solve, we want to be able to detect malware in encrypted traffic, and secondly, we want to be able to solve the problem where there is a lack of enterprise-wide visibility into encryption strength that exposes vulnerable implementations. As a result, we have enabled two use cases as part of the solution. Get an audit of your network for cryptographic compliance, and secondly, detection of malware lurking in encrypted traffic originating from the endpoints in your enterprise. So what were the requirements for the solution? The solution should ensure that the privacy aspects of encryption are not compromised. We'll also need to ensure that we build something that adapts to the changing encryption standards and automatically handles newly discovered malware. So let's look into the building blocks that will need to come together for this solution. First, we need to identify where we collect the data features. The network plays a critical role here because it gets to see all the traffic originating from and destined to the endpoints. The network will observe the traffic and collect the data features, namely the initial data packet and the sequence of packet lengths and times, for export. We'll then need an analytics engine that would digest this information and enable the two critical outcomes to be achieved, namely encrypted malware detection and cryptographic compliance. How we productize this should be of interest to you because we're the only company in the world that can do this, and it starts with the recent launch of the Catalyst 9K. The network itself is responsible for generating the metadata here, and so you don't need to install any other boxes in your enterprise. We do this by enhancing the FNF records to send the IDP and the SPLT information to the StealthWatch flow collector. In other words, you can look at this as an extension to NetFlow, or perhaps as enhanced network as a sensor. Cisco StealthWatch then takes all of that metadata, deduplicates it, stitches it with other metadata, and prepares it for a lot of analytics. Cisco StealthWatch, if you don't know what it is already, it's like a giant ledger of your digital business. Now, with ETA, it has more metadata about the security of the communication. Like, for example, was it encrypted? How is the quality of the encryption? All of that questions can now be answered. Now, Cisco StealthWatch has teamed up with Cognitive Analytics, which is a cloud-based service, and comes back with an analysis as to whether the traffic is malicious or not. Think of machine learning on a global scale that is basically helping you with the fidelity of detecting malicious traffic within encrypted sessions. Only Cisco can do this. Okay, so what we can do in summary is that we can actually leverage the network intuitive with the newest switching hardware combined with enhanced flexible NetFlow for integrated security. We can investigate threats faster compared to the industry with visibility across the network fabric and enhanced analytics and machine learning. And we can finally resolve network security incidents and mitigate malware and other vulnerabilities in encrypted traffic with higher precision. There are a couple of deployment modes that we will support in the campus. One would be the traditional wired deployments, where the 9300 will be processing traffic from the endpoints that are connected directly to the ports on the 9300. In this case, we would have to enable ETA on the access ports that provide connectivity to the wired endpoints. And we also support a second deployment mode, and this is essentially the fabric-enabled wireless deployment for software-defined access fabrics. This would allow ETA to be supported for traffic originating from the wireless clients that are connected to the network via the access points, which are in turn connected to the 9300 switch. So in this particular case, ETA will have to be enabled on the VLANs that carry the traffic from and to the wireless client. While the Catalyst 9K covers the campus wired and wireless deployments, we'll need a strategy for the various types of branch deployments. Starting with iOS XC 16.6.2, we support ETA on the ISR, ASR, and CSR portfolio. There are multiple branch deployment modes to be addressed. Branches with no direct internet access, those with direct internet access, and those with DIA via a cloud DMZ. To support these different deployment modes, we would have to support enablement of ETA on the ISR, ASR, and the CSR. In addition, to optimize the additional WAN bandwidth that would be required to support ETA fields in the modified FNF records, we added a whitelisting capability that would bypass ETA processing for a subset of the traffic. This is because we expect the ETA functions for that subset of the traffic to be applied elsewhere in the network where the exports will not require WAN bandwidth. A lot more details on the different deployment modes and the point of enablement of ETA for those deployment modes will be available in the CVD. So now that we've talked about the switch, let's look into cognitive analytics. Cognitive analytics identifies the threats with layers of anomaly detection and classification used to identify, prioritize, and describe difficult to find threats. Cognitive has a global risk map which helps provide a few key functions. It models and uses up to 20 features of 150 million malicious, risky, or otherwise security relevant servers. These features are used as input for cognitive algorithms inside the engine. And the features include domain data, whois data, TLS, certificate data, and behavioral data for each of these servers. With the integration of cognitive with StealthWatch, which happened prior to ETA, we have two key values already: extended visibility and behavioral analytics. So Cisco StealthWatch monitors flows across hundreds of network segments simultaneously. So you can actually spot suspicious network behavior. It ingests the proxy records and processes them or associates them with flow records, delivering the user application and URL information for each flow to increase contextual awareness. Cognitive threat analytics extends this approach to a global scale. The second thing is advanced threat detection. StealthWatch with cognitive threat analytic monitors popular cloud services that businesses use, such as Salesforce and Dropbox and Google and Box, to name a few, and other internal corporate assets such as ERP systems, and identifies anomalous usage of these services. This, combined with the baselining capabilities within Cisco StealthWatch, can identify if these services are being used legitimately. Now, with ETA, this simply gets even better, right? So with Cisco StealthWatch and its enhanced analytics capabilities, customers can get much better understanding of the encrypted traffic in their network and if it is actually carrying malicious patterns. Now, it does this by applying machine learning and statistical modeling for encrypted traffic analytics to enhance net flow analysis. Cognitive analytics can learn from what it sees and adapt to changing network behavior over time. ETA was launched on the Catalyst 9300 with iOS XE version 16.6.1. It's now available on the Catalyst 9400, ISR, ASR, and CSR portfolio in iOS XE version 16.6.2. It is available as part of the DNA Advantage license level on the Catalyst 9300 and 9400, while it is part of the security license level on the routing platforms. So let's now look at a demo of how all of these different components come together. The configurations on the switch, what happens on the StealthWatch flow collector, and what happens on Cognitive. So let's look into how we enable ETA on the Catalyst 9300 switch. So I'm logged into a 9300 switch that is running the 16.6.1 software version. So what do I have to do first? As you will see, it's really easy to enable ETA on the switch. The first is you have to go to the global config mode, and then you have to specify the flow collector IP address and port number. So the way I do that is pretty simple. I go into the ETA Analytics submode. I specify the IP flow export destination 10.126.71.20, and then the port number. So this is basically, the global configuration that's required. From an ETA perspective, we can actually specify the timeout as well. In this particular case, I won't do that. And then I have to go to the specific interface or VLAN on which I would like to enable ETA. In this case, I'm going to go to 10 gig 1017, and then all I have to do is ETA Analytics enable. That's it. These are the steps that you need to do on the switch to be able to enable Encrypted Traffic Analytics. So the way you verify this is you have a show platform software ETA Analytics global command, which will actually tell you the configuration information. So it'll specify the specific IP address and port number of the flow collector. You'll be able to see the interfaces on which ETA Analytics is enabled. In this case, if we don't have anything enabled on the VLAN, but if you have anything enabled on the VLAN, you'll be able to see that as well. Okay, so I have traffic going through this switch constantly, and there are some benign traffic as well as malware traffic that's going through this interface. So the way to verify that is you do a show flow exporter ETTA exp statistics, and you'll be able to see the number of ETTA flow records that have actually been sent to the flow collector. Okay, so this is all that is required from the perspective of the Catalyst 9300 switch. Okay. So let's now look into the StealthWatch management console. So this is the console where you will actually be able to visualize the two specific use cases that are enabled by Encrypted Traffic Analytics. The first is the detection of malware in encrypted traffic. Now in my packet captures, I'm actually sending some PCAPs of ransomware, which is encrypted, and the switches look into that stream, they export the metadata, it gets to the flow collector sends these metrics to Cognitive Analytics in the cloud, and Cognitive Analytics will be leveraging the machine learning classifiers to identify malware in encrypted traffic based on these fields. So this information is then sent back to StealthWatch, which is then shown in the Cognitive Threat Analytics widget here, right? Now, as you can see, the traffic that I sent was correctly classified by Cognitive as a ransomware, and it's encrypted, and this is basically detected using Encrypted Traffic Analytics, right? So the metrics that was exported from the switch. So this is essentially one of the key new capabilities that has been enabled as part of ETA, right? So this 10 here indicates a threat score, which means that there is a very high degree of confidence that this is indeed ransomware, and then you could actually take specific corrective action if you choose to do that, right? Now, if we want to get more information about the specific communication pattern that was used by this particular ransomware, you click here, you can open up the Cognitive Threat Analytics portal, and there you'd actually be able to see more information about the communication pattern that was used by this ransomware. So you'll be able to see that this was encrypted, you'll be able to see the specific URL and the port numbers and so on and so forth, right? So all of that information is available on the CTA portal. Okay, so this is essentially
how the first use case is enabled on the StealthWatch management console. The second use case is around cryptographic compliance, where a SecOps admin can actually, look into some data on SMC, which will enable them to identify the amount of, vulnerable traffic in their enterprise, that is traffic that is not encrypted, and traffic that is encrypted but is not using the right cipher suites and so on. So to be able to do that, we have to go to this Analyze tab, click on the Flow Search button, and I'm actually going to be searching for the last hour, the flows that were actually reported by the switch for the last hour. And once I do that, I'm actually going to be able to see like a whole bunch of flows that show up. Now the fields here, right, the encryption TLS version, the encryption key exchange, the algorithm and the key length, and the authentication algorithm, these are all the fields that have been additionally enabled in StealthWatch because of the new exports from the switch. Okay, now let's filter this out. If I were to click on the filter button and if I go down, I'll actually be able to see the number of flows that actually did not have any encryption, which is about 1829. The number of flows that used TLS 1.0, the number of flows that use TLS 1.2, and so on. So let me just click on TLS 1.2, and you'll actually be able to see the specific details about the encryption algorithms and so on. But from a SecOps admin perspective, the key takeaway for him is that there were a significant percentage of the flows that were unencrypted, and so now he'll actually have to take specific actions to ensure that those endpoints start using encryption to secure their traffic. Okay, so the two use cases again in summary: malware detection in encrypted traffic and cryptographic compliance, and both of these are enabled by the exports from the Catalyst 9300 switch and are actually shown visually on the StealthWatch management console.
So how do we enable ETA on the routing platforms? It's very similar to the way we do it on the Catalyst 9300 and 9400. You will need to enable ETA Analytics command globally to specify the flow collector's IP address. On the routing platforms, in addition, we will support the whitelist command, which will indicate the subset of traffic for which ETA processing can be bypassed. This is because it would be done at another point in the network, which would help optimize the WAN bandwidth consumption. After this, you would just need to enable the ETA Analytics command on the interface. There are a number of show commands available that would show the stats with respect to the ETA exports, all of which will be documented in the CVD. So let's round this off with some of the key takeaways from this session. Encrypted Traffic Analytics leverages the power of network-based telemetry and cloud-based analytics to solve some very difficult to solve problems for customers. Number one is detection of malware in encrypted traffic without decryption, and secondly, doing a cryptographic audit of the network. Now this enhances Cisco's network as a sensor capability by collecting threat-centric metrics from the network, and therefore it helps in reducing the time to detect malware significantly.